Okay. All right. So today, we are going to continue some more discussions on photophysics, basically fluorescence, phosphorescence, and the related features of molecules in the excited state. In the process, we are going to talk about what is called as the supramolecular photochemistry, which involves use of organized assemblies to control the excited state chemistry. Okay. Before we talk all that stuff, I wanted to go back a little bit and then tell you, we talked about mainly two things: the excitation and then emission of compounds. So that will be radiative process. Radiative, it means something is going in, something is coming out. That is in the form of light. So when you take the molecule to the excited state by shining light on the compound, in addition to emitting light, they can do other things. So everything is competing with each other. So I just want to give you an idea what are the other pathways by which the molecule can disappear from the excited state. So the fluorescence is always competing with the other pathways by which the molecule will disappear. Okay. So for example, the molecule we talked about the ground state, singlet, triplet, and then the phosphorescence, fluorescence, all these stuff. Okay. So here, if you take a molecule in the ground state, the molecule is going to be in the S0. 0 means that is the starting point, and then that S means singlet. If you shine light on this molecule, it will absorb the light and go to the excited state. Again, S means singlet, the 1 means first excited state. Okay, there are more people coming in for some. I don't know whether all of you were there in the class yesterday, day before, but I cannot remember the face. Whether I hope you can follow very quickly what I am talking. Okay. So the 1 means the first excited state. There could be S2, S3, S4, like that. So it all depends upon from which orbital the electron is getting excited and where it is going. And the gap between the S0 to S1, this much, if you provide enough exact energy for that, it will go from S0 to S1. If you provide energy for S0 to S2, it will go from S0 directly to S2, not S0 to S1, S1 to S2. Okay. Now, after it goes to the S1, this molecule here, it can emit light, that is the fluorescence. That is, this is a singlet state, this is also a singlet state. There is no change in spin. Both the electrons, whatever way it was here, it will come back in the same spin. That's why it is the singlet. Both are singlet. It is very important that during the excitation or emission, the spin does not change. If it changes, the rate constant will be slow. So this one is the fluorescence, and we talked about this. This is the emission, this is the absorption. We talked about the extinction coefficient and the rate constants. These are the ones that tells you whether this is going to happen or not. If the number is small, that means it is not. It is going to be very slow. Okay. In addition to this emission, there is something like this kind of line that tells you it is called as radiation-less transition. This is a transition from here to here or from there to here. That is a transition. So when it is emitting light, we call them as radiative transition. That means the light is coming out. And this one, which is written like this means radiation-less transition. The molecule is coming from here back to here, but it is not emitting light. But that has that 100 kilocalories or whatever energy it has got, it will give it away in small pieces. like 5 kilocalories, 2 kilocalories, 1 kilocalories, pretty soon it will come back here. That one is called as internal conversion, okay? And that has a different rules that, let us see whether if we have time we can discuss, if not, it is not that important. So from singlet the molecule will go to the triplet. This singlet triplet, as you see here, it also has got number 1. That means that is the first excited state, but the first excited state, it has got a triplet spin. That is, it has a spin which is not, the 2 electrons have the same spin, they don't have the opposite spin. So that is the triplet, that is the first triplet. The second triplet is over here, third, fourth, and all this. So going from here to here, this is a singlet and this is a triplet. This particular process is also put as a wiggly line. That means going from here to here, there is no emission. The molecule goes from this place to that place, but loses this much of energy, that is the energy corresponding to this, it will go into the solvent and then it will come here. So going from here to here, tell me what does that involve? First of all, it has to lose the energy. That much of energy it has to release, that will go into the solvent. But then this one is S1, that one is T1. So going from here to here, will it be slow or will it be fast? Or what is the thing that has to happen? So can you tell what is the thing that has to happen? Okay, so this is a singlet state, that one is a triplet state, and the triplet state is always lower in energy than the corresponding singlet state. And the triplet from here to here, the gap is, it can be 10 kilocalories or 45 kilocalories, depending upon the configuration. So to go from here to here, it doesn't emit light and go. It basically loses the energy in the form of heat to the medium, and then it will land up here. So when it is coming from there to here, what has to happen? That is the question. What has to happen? Yesterday in the afternoon, I think I thought you all answered a lot of questions. So I was very happy. That seemed like you understood what I am talking about. So now, if you answer this question, I will be happy also. Okay? So tell me what is the thing? Okay. So this is a singlet and this is a triplet. They have the same electronic configuration, let's say n to pi star. But then, so the electrons are the same set of orbitals. There is one electron in the n, one electron in the pi star in both the cases. But then this one is of lower in energy than that. So what makes it lower in energy? So if it wants to go from here to here, what the molecule has to do? This is not a difficult question. This is an easy question. Sometimes you think it is more difficult than it is. Okay, so I am happy at least to get started. So from here to here, there are 2 electrons. There is one electron in the n, another one in the n pi star, and these 2 electrons have opposite spin. That means it is here. If it goes here, the 2 electrons which are opposite, it will have to change this. One of them has to change the spin so that it becomes the same spin. They both becomes alpha alpha. So that process is this rate constant here. That rate constant will depend upon sometimes slow, sometimes fast. It depends upon the number of factors. Okay, so you can see now if you put the molecule in here, one of the things that is going to do is the emission. The other things are going to be like this, that is the internal conversion and then this is called inter-system crossing, because it is crossing from singlet to the triplet. So that is why it is called inter-system crossing, or you can see ST, singlet triplet crossing. So this fluorescence rate constant he is going to be competing with this and competing with that. Sometimes there is a chemical reaction. So, this molecule from here, it will go to some other product. So, that is the third rate constant, that is the rate constant here. So, this number has to be larger than this one, that one and that one. If it is smaller, then you will not see any emission. So, to see the emission, it has to be larger. Okay? And then once it goes to the triplet, it comes to the triplet, and we said the triplet you can go from ground state directly to the triplet, but then this number here, the extinction coefficient, is going to be tiny, small, because this one is a spin forbidden transition going from here to here. This is a singlet, that is a triplet. This also is a singlet and a triplet. This also is so these transitions are very slow. So, the absorption is going to be very small. So, you cannot directly populate the molecule to the triplet state. So, if you shine light on the compound, it will not go to the triplet state, because the extinction coefficient for this will be about 10 power minus 1 minus 2 like that. So, ideally it should be 10 to the power of 4, 10 to the power of 5. So, it is very large, it should be a large number. So, that will be the case here, but not for this. But the molecule can come to the triplet. If you put it here, it will come to here, but not, it will not go from here to here. Okay? So, once it comes to the triplet, it will emit light. Do you remember when it emits light from the triplet, what is it called? Okay, what is it called? Simple. You know, these are all not complex questions. Okay, there are, you know, we talked about Excimer emission, delayed emission, and then ticked emission. There are very many emissions we talked about, right? One of those types of emission is this one. What is it called? Huh? Okay, phosphorescence. Okay, so it is called phosphorescence. And then, so this phosphorescence is the one you can see with your eye, or the machine can see. Okay? And then, but this phosphorescence, just like here, this molecule can come back down by this process here. That is called again internal conversion, or it is, you know, depending upon the, here it is going from triplet to singlet, it is called TS. Okay? So, this process is basically, if it has got 70 kilocalories, instead of converting everything into light, it will convert everything into heat. And then this process is, so this rate constant, it tells you whether the triplet, how fast it is converting the energy into heat. This one tells you how fast it is converting the energy into light. So, this one has to compete with this to be able to see the emission. If this one is smaller than this, the emission will be very weak. If this is larger than that, then you will see a good emission from the compound. So, there is always competition between various things. And then when it goes to the triplet, again it can undergo a chemical reaction. So, this rate constant, that is this one, is competing with this and competing with that. Okay? So, it is very important for a given compound. If you are, let's say, you are interested in pyrene, you should know what is the energy of the singlet, what is the energy of the triplet, what is the radiative rate constant, what are the other rate constants. So, from that you can tell whether you will be able to see the emission or not see the emission. Okay? So, this is the diagram, you know, I told you yesterday, Jablonski, and these two people, they also had something done similar to this, but still this is the diagram is known by his name, not by these people. Okay, this is his father and son, they had worked together on these things. Okay, so for every compound, you will have something like this. It is not, the numbers are not fixed. It is going to change from compound to compound. It will change. You want me to close the door? Okay, so because you need to know the numbers of these and these and that, so that you can tell whether you will see emission. Okay. Here is one compound, chloronaphthalene. So chloronaphthalene, okay, you can see all these things here. You know, the picture that I showed you last one, the same kind of picture, but now it has got a compound, some molecule there. Okay. So now, for example, this is a straight line, and this is a wiggly line, straight line, and then this one. Okay. Of these things, tell me which one is fluorescence, which one is phosphorescence. Which one is fluorescence, which one is phosphorescence. Okay. 1, 2, 3, 4, 5. Okay. Tell me which arrow represents fluorescence. Which one? Okay. Is it this? Okay. That one? Okay. Fluorescence, correct. One, two, three, four. Which one? 4? Okay. So this is fluorescence and this is phosphorescence. Okay. These numbers here, that tells you the rate constant, that is how fast the emission will take place. Or okay. So if you see the emission rate constants, this is 1.9 second minus 1. This is 3 into 10 to the power of 6 second minus 1. Okay. Tell me which one is faster or more efficient, this one or that one? Fluorescence. Okay. So this is 3.10 power 6, this is 1.9 in 1.9. So obviously this is a lot more, about almost 10 to the power of 6 times more than this one. So the fluorescence is, you are able to see, you will see the fluorescence much more strongly compared to the phosphorescence. Okay. Now this fluorescence is competing with this number and that number. The fluorescence is, this is here, this is converting 90 kilocalories of energy between the energy here and here is 90. So that 90, it can be converted into light or it can be converted into heat. Whether it is converting to heat or light is controlled by this number here. If it wants to go to heat, 10 to the power of 4, wants to go to light, 10 to the power of 6. Okay. So tell me which of these two is more efficient, going to heat or going to light? Heat is more efficient. Okay. Let's ask somebody else also. Is okay. The efficiency depends upon the rate constants. The larger the number is more efficient. Okay. So here we are comparing two things. One is the fluorescence, another one is radiationless transitions, and the numbers are here for these two. Okay. So tell me which one is more efficient. Which one is more efficient? You know, this is not okay. So it's, this is 10 to the power of 6, this is 10 to the power of 4, which is larger, bigger number. This one is bigger number, so this is more efficient than that. Okay. So the molecule will be able to convert the energy that it has got into light more efficiently than it will be able to convert into heat. So between the two numbers, so you are going to be getting a lot of fluorescence from this compound. Okay, but this one, if you notice, it is also competing with the intersystem crossing from here to here. That number is 10 to the power of 7. So this molecule is competing, this one or competing this one or competing this one. Now tell me, the fluorescence is going to be compared to this, is it weaker or stronger? Okay. So this molecule has got, there are 3 different routes. This can disappear by this way, or that way. So of the 3 paths, this is the slow, this is okay, this is faster. Okay. Whatever is the faster one, that is the way it is going to go. The faster one is 10 to the power of 7, this is 10 to the power of 6. So between these two, this one is faster. So more and more of the molecule will go here, and less molecule will be here, but it still is going to be like 0.1, because 10 to the power of 6 divided by 10 to the power of 7, it will be 10 power minus 1. Minus 1 is 0.1, right? So this molecule will emit the fluorescence, but the fluorescence is going to be not 100%. It is only about 10%, because 90% of the molecule is going from here to here. As you can see, 94% ends up to the triplet state. Okay, once it comes to the triplet, you notice the energy of the triplet and the energy of the singlet, they are different. This is 59, that is 90. So about 31 kilocalories more. The singlet is more by 31 kilocalories with respect to the triplet. Okay. So once it comes to the triplet, now it can come down, or it can go through this way. Look at the rate constant for this. Tell me whether the two are almost the same or one of them is faster. Which one is faster?
The right one.
Okay. So there are 2 rate constants, 1.9 and 1.4. They are almost the same. Okay. So it is going to be, when it comes to the triplet, it is going to be almost, you will get 50% emission and about 50% will go away. So you can see the number here, 57%, 43%. Okay. Tell me which one will have a longer lifetime. Longer means lives longer. Okay.
The
Left is this one. Longer lifetime. That means it is going to live there forever, for much longer than the right. So you think this is going to be living longer? Is that what you are saying, or?
you mean the fluorescent lifetime and the phosphorescent lifetime?
No, it is actually, it means the lifetime of the molecule in the excited state here and the excited state here. Okay. So fluorescence and phosphorescence lifetime are also pretty close. It will be very close.
The triplet lifetime is longer.
Triplet lifetime is longer. Okay. So the lifetime of a molecule is basically going to be, so you take this. So the lifetime is usually put like this. You will see something like that, and it will be equal to 1 over the various rate constants, fluorescence, and then they don't have a name for this. So it will be intersystem crossing and then internal conversion. This is for the singlet, and for the triplet it will be like this, 1 over K phosphorescence, K the triplet going to the singlet, and then these two. Okay, there are only 2 things, and then there is always a reaction. Okay. So the lifetime, the number is on the bottom. So if you put this number on the bottom, it is going to be 10 to the power of 6. This is going to be 10 to the power of 7, and this one is going to be, this one is 10 to the power of 4. So these numbers, and for this number is 1.4, 1.9, and then we don't know about the reaction. So what happens is, this is going to be longer, it will have a bigger number, and this one will be shorter. So, usually what happens is the triplets will live for a few seconds, that is 1 over, let us say 1 over 2 is about 0.5 seconds. So, it is a long lifetime. And then this one is going to be 1 over 10 to the power of 7, that is going to be 1 over lifetime will be 10 power minus 7 seconds. It is a shorter time compared to this one. Okay. Okay, this is for a molecule like naphthalene. So, these numbers are not always the same, it will change. That is where you have to read the book, because if you understand the theory, what is controlling these numbers, then you can guess. If you do not know the theory, then you just have to depend on these numbers. Okay. You go to this compound, this is benzophenone. Okay. Benzophenone is basically this compound. This is benzophenone. Okay. So, now if you look at this benzophenone, there are 2 different types of excited states. 2 different types means 2 different electronic configurations. So, if you look at here S1, it is N pi star. That means oxygen has got a lone pair, one here, one here. One of the electrons is going from N to a pi star orbital, that is this one. And then there is another excited state which is pi going to pi star, that is this one. Okay. Now, you look at all these numbers, okay, number for the internal conversion and then the fluorescence, intersystem crossing. Okay. I do not know whether you remember the number that the last slide. In this compound, what is the biggest difference between the last compound and this compound? Biggest. Okay, I will give you, just look at these numbers for a few minutes, remember, and then go to the next slide, figure out or note down these numbers if you want, and then tell me which one is the most okay. So, I am going to go to the next slide. Tell me which is the most important number. It changes very dramatically between the last one and this one. Which one is changing? Okay. Okay, let us see, for example, this is the singlet state. The singlet state, this is the fluorescence rate constant 10 to the power of 6, and then the internal conversion 10 to the power of 7. Okay. And this one is intersystem crossing, which is 10 to the power of 11. Okay. Between 1, 2 and 3, which of these numbers for the last compound is the difference is large? Remember anyone? You remember which one? Okay, let us go back. See, the intersystem crossing for the last one is about 10 to the power of 7, and this compound is 10 to the power of 11. 10 to the power of 11 is a very large number, and the last one is 10 to the power of 7. So, the difference between the last compound in this compound is about 10,000 times faster. So, the that is going from singlet to the triplet for this compound is much faster than the last compound. So, you need to know why this compound is faster. That is where you need to understand some theory about intersystem crossing, spin orbital coupling and all this kind of stuff, which I do not know whether we will see whether we will talk about those things. Tell me in this compound whether this molecule will show a good fluorescence or no. No? How did you decide that?
Because the S1, the singlet 1 to the triplet 2, the number is high.
Okay. So, we have to compare this number with that number, and the difference is about 10 to the power of 5. 10 to the power of 5 is 100,000. Okay. So, this one is extremely fast compared to this. So, the fluorescence is going to be very weak. For the last compound, if you notice, this one is 10 to the power of 6, that is 10 to the power of 7. but the difference is only about 10 times. So 10 times means you will get at least 10% of emission from here, and the next compound is not going to happen. So now, since this is faster, this molecule will come from here to the triplet, and from the triplet it will emit. Okay, and then the numbers you can see, the emission is about 1. This is the internal conversion, and this is the phosphorescence rate constants. This is 10 to the power of 2. This is about 1.7. So between these two, you think phosphorescence will be more or less? So this compound will phosphorus or no? Phosphorus. It will phosphorus. It will phosphorus. Okay. So here, for example, this number is about 10 times this. So this rate constant is, this process is going to be able to compete with this. So you can see phosphorescence from benzophenone. But the last compound, if you remember, these two numbers are almost the same. So the phosphorescence from this compound is going to be, you will see something, but it's not going to be that much efficient. Whereas this compound, it will be efficient. So that's why it is important to know these numbers. So you have to know, and many of these numbers you will find in the handbook. So you don't have to really measure these numbers. But if you know the number, then it will help you to know what's going on. Okay. So this is basically the whole thing about fluorescence and phosphorescence and any types of emission. Okay. The thing that we need to understand is this: what is this line means? This line looks a little different from that line. What exactly is that? How does the rate constants vary from compound to compound? That we'll talk on Monday. Okay. So now I want to talk something else. Okay. Now, okay, all these things have numbers, right? But the goal is, suppose the last compound, it doesn't want to emit it doesn't want to emit phosphorescence, and this compound doesn't want to emit fluorescence. Our goal is to do this different. Make this compound emit fluorescence, and the last compound you make this emit phosphorescence. So the thing it doesn't want to do, you make it do, because that is one way to control these molecules. Otherwise, the molecule is going to do whatever they want to do. So somehow you will have to have some handle so that you can make them do what you want to do. So that kind of thing I'm going to talk about for the for some more time today. Okay. So you take, for example, this is molecular photochemistry. Basically, you take a molecule, put them in a solution, and then you observe the chemistry. So whatever it is chemistry is going to come out, it is the inherent property of the molecule. So all the numbers that we had, that is the way the molecule is going to do. Okay. So now, if you want to alter the chemistry, what you do is you put the molecule in a very small place, you sort of squeeze the molecule, confine the molecule, then it will do a different thing. I don't know, when you were a small kid, like 20 years ago, like 2-year-old, very small, and then you run here and there all over the place. Your grandparents or grandfather or mother, father, they are not happy. So they want to control you. They want you to stay in one place. Then what they will do is they will put you in a small room so that you cannot run around too much. So the same thing will apply to the molecules. If you let the molecule free, they will do whatever they want. But if they put them in a small place, then you can tell them what they should do. Okay. So what happens is, you take a molecule. This kind of chemistry, putting a molecule in a small space, is called as supramolecular chemistry. That means you put a molecule in a confined space so that the molecule does not have a lot of freedom. If they don't have a lot of freedom, then the chemistry is going to be, you can have some control. Otherwise, there is no control. You don't have a control. Okay. So R is the ground state, irradiate, it goes to the excited state. In the excited state, it fluoresces, and then it undergoes intersystem crossing, all the things I showed you before. Or also it can undergo a chemical reaction to give an intermediate and then give a new product. Okay, you don't like any of this stuff. You want the molecule. If this molecule is left alone, it will not show fluorescence. But you don't, you want them to do you want it to fluoresce. So what you do is you take this molecule, put it inside a small place. Now if you excite this, it will go here. Now it is still sort of sitting very confined, but now its inherent property will be changed. And when it does change, it might start seeing fluorescence from here, and then a reaction will go, but the reaction will give you only 1 or 2 products. Okay? So this is what is called as supramolecular. It's a very popular topic. Okay. So supramolecular photochemistry in 1987, these 3 people, they got the Nobel Prize. Okay, and so these people, what they did was, you probably use crown ether. I don't know whether you are familiar with the crown ether. Anybody knows what is a crown ether? Crown, and then it is ether. Okay, so if you want to take, let's say, potassium permanganate, KMnO4. Do you know what is KMnO4? You must know. Potassium permanganate. Okay, I will write down. Okay, potassium permanganate. Tell me, in what solvent it is soluble? What is the solvent in which it is soluble? Huh? What is that? H2O. Yeah, water. It is soluble in water. Okay. So suppose you want to, okay, it is soluble in water. All right, that's a big deal. But you want to dissolve this in benzene. Okay. Then how would you dissolve this in benzene? You think it will be soluble in benzene? Potassium permanganate is like sodium chloride. Sodium chloride is something that we eat. So sodium chloride is soluble in water. But sodium chloride is not soluble in hexane or benzene or something. But if you want to dissolve this in hexane or benzene, you can do it. So, but that means you have to change the property of this potassium permanganate or sodium chloride or whatever. Okay. So what you do is, this is what he did. He is Charles Pedersen. He was working for a DuPont company. So you take what is called as crown ether. He made this kind of compound. You might have studied these compounds. Okay. So when you have this compound, the potassium K plus, it will complex. This is something that when you do the sensors, when you are doing sensors for potassium, sodium, things like that, you will have this kind of compounds attached to something, like yesterday I showed you. So this molecule, the crown that is here, it will complex to potassium. Whether it is water or whether it is hexane or benzene, it doesn't make any difference. So this K plus will go inside this. And then when, for example, you take this potassium, this molecule is soluble in hexane or benzene. This molecule is an organic compound. It is soluble in hexane or benzene. And then you take it in hexane or benzene and add the potassium permanganate, which is not soluble by itself. Now the potassium plus will complex to this. So it will become, that part will be dragged into the benzene. So the K plus, if it goes in, the MnO4, which is minus charge, it will automatically come, because K plus and MnO4, they always want to be together. So if the K plus goes in, MnO4 will also go in. Then what happens is the potassium permanganate becomes soluble in hexane or benzene. Okay, the potassium permanganate, if you have it in your lab, try. It will not be soluble in hexane or benzene. But on the other hand, if you add a little bit of this crown ether, then that will become very, very soluble in benzene. So that is called as purple benzene. The benzene which is purple only with potassium, because potassium permanganate is in the benzene. Okay. So this kind of chemistry basically what happens is you are taking potassium plus and then it is confined with the help of this compound. Now its property completely changes. Normally it would not be soluble in benzene, okay? And similarly, for example, this compound or this compound, they all do this something very similar. You can put a molecule inside another molecule. So if you have, for example, one molecule, it has its own property, and then put this molecule in another bigger molecule. Now the property of this molecule is altered by a package that is going around this stuff. So that is what is called as supramolecular chemistry. And these three people, they sort of started this area in 1970s, and they got the Nobel Prize in 1987. This is John Mary Lane, is a very famous guy. Charles Pedersen and Cram, they both died maybe 10-15 years ago. Okay. Today, a lot of people work on this kind of topic. Okay. Okay. This one, for example, have you heard of any of these people? They come to these people come to China very often, actually. So Fraser Stoddard, and then Feringa and Jean-Pierre Sauvage. Okay, they got the Nobel Prize a couple of years ago. So this one is very similar. You take a molecule and alter its properties with the help of another molecule. They will make a molecule move. So these are called as molecular machines. So if you have a small molecule, they always sit around. They don't do anything. They cannot walk. But then these people, with the help of light, they made this molecule walk around. So this molecule, if you put it here, if you have 1, 2, 3 molecules, they can move faster. One can move faster than the other one. So that is always, in the nowadays, every year there is a race, like a car race. Which horse goes faster or which car goes faster? They have a race for which molecule moves faster. So that is done by this kind of technique. That is, you put a molecule inside another molecule, shine light, and then it will just keep walking. Okay. And then, so this is the kind of chemistry I just want to talk a little bit. And the supramolecular photochemistry was, for example, Breslow, John Mary Lane, Nick Turreau. These are the people who pioneered this topic. Okay. And if you want to study these things, I think I sent the PDF. I think it is the last several PDFs are supramolecular chemistry. Okay. So this is the same book that you have, but it is a chapter number 13. And then there is a book here, and there is another book. So all these books are useful if you want to understand a little bit about supramolecular photochemistry. Okay, in this supramolecular, like what we did, for example, potassium permanganate, what we did was we put the K plus inside another one, like the crowd ether. I don't know whether you have, the people who do work with the sensors, they probably use crowd ethers. You probably don't know it is a crowd ether, and crowd ether is a molecule, and then it is with a tag. You attach it to anthracene or something, and then when you shine light, anthracene will not emit. When potassium plus or something comes, it will come to this. Okay. Now, how do we do this? If you know the basic principles, you can understand how to alter their chemistry. Okay, here there is a molecule here excited, and then it gives a lot of products. Okay, you want in a chemical reactions, you want to get only one product. If you get 5 products, that is not very good. That means you have to do a lot of separations and all this stuff. So how to make this molecule give only one of these? Maybe you want only this or something like this. So the way we would do is we take this molecule. Normally you dissolve this in some solvent and then shine light, and then you look at what happens. Now instead of putting in the solvent, you put this compound inside another structure which is very small. So the molecule is sort of confined in that small space and shine light. Now it will behave differently from here. Okay. Okay. So, if you tell me, suppose you have a molecule, let us say you have naphthalene. Naphthalene is in the gas phase, and then you take naphthalene in solution, and then you put naphthalene inside a protein, where in which of these three naphthalene has a lot of freedom, which one is, it has got more freedom than anywhere else. The more free something is, it is likely to behave bad. If you have, see, I am sure many of you who are here, when you go home, you behave a little bit different from when you are here, because here there is nobody to control you. There at home, father and mother are going to put some strict rules. Okay. So, if you take an naphthalene gas phase, and then in a beaker of some solvent or inside a protein, where the naphthalene will be able to move around more freely. This is
inside the solution without adding the protein would be more freedom.
Though it will have more freedom, not in the protein. Okay. Okay. So, if you take naphthalene, actually it will have a lot more freedom in the gas phase. In the gas phase, naphthalene is there, and then there is nothing around the naphthalene, so it can go around more easily. And in solution, it will have lesser freedom than in the gas phase, but it will have more freedom than in the protein. So, in a protein is a big structure. Anywhere it turns, there is going to be another bunch of molecules or polymer strings. So, what will happen is, in the protein, the naphthalene will not be able to move around, whereas in a solution, it will be able to move around, whereas in the gas phase, it has no problem. It is going to be running around all over the place. So, the molecule, more freedom it has got, the reaction is going to be less selective, or for example, even emission is going to be a bad news if it is in the gas phase compared to if it is inside a protein. Okay. So, that is what happens. So, as the reaction, as this becomes less and less free, everything becomes more and more selective. You do things which is only essential things you do, not everything that you want to do. Okay. You take, for example, all these proteins. We talked a little bit about some of these things. Rhodopsin, there is a small molecule here. Bacteria, rhodopsin, another small molecule, and this is a photoactive yellow protein, another molecule. Green fluorescent protein, a small molecule. So, all these big things are just a protein. It is only to make this molecule, just confine the molecule. So, you squeeze the molecule. Now, for example, this molecule here, which is a green fluorescent protein, if you take the molecule, put it in a solution, there is no emission. If this molecule is part of the big protein, then you will see a bright emission. So, that is actually what the fish use. These are the jellyfish. They use this compound, and that is why it is called green fluorescent protein. If this molecule is part of the protein, then you will see the jellyfish is very bright. When it is not part of the protein, then you will see there is no light. So, when something comes very close, it will push this compound inside the protein, then it will be very bright. The other one will get scared and go away. Whereas, when it is nobody is nearby, this molecule will be outside. Okay. So, basically what happens is, in here also the similar kind of phenomenon. So, when you take a small molecule, if you put it in an organic solvent or in water, the chemistry will be much less selective compared to putting them in a place where it is highly confined. So, you do not need a protein to make a molecule, to squeeze the molecule. What you can do is, you have to find something which is easy to make, not like this. These are not that easy. These are going to be pretty expensive operation. So, all you need is figure out this molecule is stuck here, and immediately surrounding that molecule, that area is going to be confined. Okay. So, there is a whole bunch of these kind of molecules, which are, you can see there is a small hole here, and there is a hole here, and something. So, if you put a molecule in this place here, for example here, now the molecule, if you take a naphthalene in water or in some solvent, it is going to go all over the place. Now if it is put inside this place, it cannot go anywhere. Everywhere it turns, there is this cyclodextrin structure is around the naphthalene. So what it will do is it cannot undergo this internal conversions, and all these fluorescence will go up, or the reaction will become very selective. So there is a whole bunch of structures like this. Okay, you see here cyclodextrins, cucurbutyls, octacid, calixarines, micelles, zeolites, dendrimers. Does any of these things, you can tell me whether you have read any of these kind of structures? Tell me, I know this one, Tell me which one, okay?
I know about Dendrimers.
Which, you know about what?
Dendrimers.
Dendrimers, okay.
Micelles, crystals also.
Okay, all right. So let's find out whether anybody else knows anything else. Okay, so he knows 3, okay? At least you should know 1. Which one do you know? Which one do you know? Have you heard of micelles before? Micelles. You heard of micelles? Okay. Have you heard of cyclodextrins? Okay, let's wait these people. Cyclodextrins, anybody? No? What about, for example, zeolites? Zeolites? No? Okay. The micelles is basically soap. Every day you take bath, I think, and you use soap. The soap is actually, like a potassium permanganate. Like, dirt is inorganic material. It is not water soluble. So if you take shower, if you have a lot of junk on your body, it is not going to go away because it is not dissolving in water. But on the other hand, if you take micelles, if you notice, the inside of the micelle is inorganic, it is organic, it is a long alkyl chain. Outside is charged species, so this whole thing is water soluble. Okay. So now if you have oil, after you eat a lot of Chinese food, you have a lot of oil in your hand and then maybe in your shirt, somewhere else. Now if you want to get rid of the oil, just washing in water is not enough because that oil is not water soluble. So if you put soap and then wash it, what will happen is the oil will come out, and then the oil is soluble only in the organic part. It is not soluble in the water. So inside has a different property from outside. So when you put a compound and then add this little bit of soap, the organic compound will go inside. If you have a lot of water with oil, and then this will go inside here. So the molecule that is going in, it is sort of confined within this small space. So now the organic compound is trapped here, so it cannot go to the water. So once it is stuck here, the area that is available for it is very much small, so its behavior will change. Okay. So similarly, for example, look at here, calixarines. There is a big, like a, I have not seen anything like this kind of thing that you eat. See, in America we have called donut. You have donut shops, right? The Dunkin' Donuts you have, or I don't know. Donuts will be looking like this. Yes, a structure like this. In the middle there is a hole, and then this one is sweet. Okay, so here there's something similar. See, this is a donut. Middle is a hole. There is an empty space. This compound is water soluble. If you have an organic compound which is not water soluble, that can be pushed to go here. So once it goes in here, all these structures are very similar. 1, 2, 3, this one, they all are very similar. They are all water soluble. And more important thing is this place that is empty space, the organic compound that is not water soluble, that will go inside and stay there, because it does not want to be in water. If it goes inside and stays here in any of these places, see, now it looks very attractive. So outside looks pretty bad. So it goes inside, but once it goes inside, it does not want to come out, but once it goes, there is a space is very small. Now so it has to be unhappy, but it will stay there. If it comes outside, it will die, because it is all water. It will just submerge. Okay. So these types of compounds are used, for example, to take a molecule and confine this in a small space, and then you activate it with the light, and then what they do is different from what they would do if it is in regular solution. Okay. So micelles, all these things are pretty common things. So there are lots of structures like this. Okay. I will show you quickly. I will show you a few things, and then we will take a break. Okay, micelles here. This is a micelle. You know, if you go to some biochemistry books, you will see these kind of structures. So micelles looks like a big ball, and the ball outside is all negatively charged. Inside is all like hydrocarbons. So this part will make it water soluble, like a bubble. The bubble outside is water soluble. The bubble inside is organic. So it is a tiny bubbles. Now if you have, since it is organic, this organic compound wants to go there, because outside is all water. It does not want to stay here. So now it will go inside. Once it goes inside, they don't know. There is not enough space. There is going to be a very tiny space. Now they are trapped in that tiny space, and then you can do something with them. Okay. So this is a micelle, and there is something called dendrimers. Dendrimers is somewhat like a micelle, but dendrimers are covalently linked. So it is harder to make. So it takes a lot of tedious synthesis. Okay. So the dendrimers looks like this, with a small. It can be a small, bigger, and bigger balls. Depending upon how much size you need, you will make these things. Okay. These are expensive. This micelles is cheap. You can buy in my hotel. I get it free. Okay. So they give me everyday soap, but you know, these things are pretty expensive. And then, okay, this is so see here, these kind of structures, the outside, the periphery, you can make it water soluble, but inside this there are some space, like an apartment. There are various small rooms in which you can push the molecule, and then so once the molecule is pushed here, they cannot go outside. So the chemistry is going to take place only in this space. So that now the chemistry is most likely be different from if it is free. And here, this is cyclodextrins. Cyclodextrin is you can buy. You see the so it comes in different sizes. This is like a ball, you know, small. So small, little, medium, larger. Because naphthalene you want to put, it might go here. Anthracene might go here. And then if you want to put anthracene here, there is not enough space. So you have to look at the size of the molecule and then buy the right size. And then once it is put in here, it is going to be different. Okay. And then this is called cucurbutyls, something similar. But only the idea is the same for all these compounds. The idea is find a water soluble material which is empty, which has got an empty space inside, and then you push your compound inside that. Okay. And this is octacid, and this is an inorganic material, palladium nano cage, and then this is made by Fujita, and there are something called zeolites. Okay, zeolites are very popular. They are catalyst. This is used in industry like oil, petroleum industry. The zeolites are used. The zeolites, this guy, he found it in 1700s. Okay, this was, for example, these are called as boiling stones, basically. So if you have, the guy was walking in a beach, and then he found some stones were jumping. You know, they are jumping around. So then he found out, how can a stone jump around? This is like your monkey story of this Who is the guy? Oh, he's from here, Sion. The guy, I don't know what's his name. There's a big statue in the downtown, not near the temple, near the, I think we call him as Yuan Swan. You know, he's a Chinese monk who went to India, and then there is a story, TV stories like a monkey something, Monkey King. Okay, so this guy, when he saw the stones are jumping, then he realized there is, how can a small, if this coffee cup, if it's just jumping around, you are worried why this coffee cup is upping. So these zeolites, what happens is this is as found in nature, and they all contain empty space. See, this is a zeolite, this is like a small rock, but inside is empty, but it can store water. If the outside temperature is hot, and water will boil, and then the stone will jump up and down. So this is, now for us what we do is, we can take the zeolite, and this is an empty area in which you can put an organic molecule, and then you can do some photochemistry with these things. But once you put a molecule here, it cannot get out of this place, it is stuck there. Okay, so this is a zeolite. It comes in various sizes. You can see the various holes and shapes and all this kind of stuff. So this looks like this. The zeolites looks like a nice crystals, but inside the crystal there are millions and billions of these holes. Okay. All right, we will stop here. For now it is 35:50. It's 9:50, right? We will come here 9:50, 9:50. Okay.